So in section 6.1, we're going to try and find the area between two curves. So in this case, we're looking at these two curves, curve of f of x equals x plus 4, the curve of g of x equals x squared minus 2x. I hope you know which one is which. Of course, I think it's pretty clear. One's a straight line, one's a parabola. But historically, this was a little bit of a challenge because it's not a regular geometric object. It's not a circle, it's not a square, a rectangle, a triangle, trapezoid, etc. All these things for which we have formulas. So historically, what we did to try and find the area was we would try and approximate it. And we'd approximate it with a bunch of rectangles. So let me draw a few rectangles here for us. So we've got 4 rectangles here. And what we could do to get an approximate area, we find the area of each of these rectangles and then add them all up. Okay, so that's fine. Nothing wrong with that. Except, at least in this case, does it look like a good approximation to the area? You know, all these rectangles added up, is that a good approximation to the area between these two curves? I'm not so sure. Not so sure it looks good. It's probably not horrible, but it's probably not, you know, really good. What do you think we could do to improve the approximation here? Any suggestions?
More rectangles.
More rectangles. Awesome. Yeah. So let's increase the number of rectangles. And as you do, you're taking a limit. And what's going to happen is that that limit is going to change the sum to an integral. So you're starting out with the area between, or the area of one rectangle, which is your top function minus the bottom function, times the width. Now that width character is going to become a dx as we take the limit. So we're going to sum that up for all these rectangles, but as you take the limit, as you increase the number of rectangles, that limit simply becomes an integral. And we're going to integrate from a to b, top function minus bottom function times dx. So let's give that one a shot here for this particular one. All right, so let's write down our formulas, our functions. Y equals x plus 4, and y equals x squared minus 2x, and we'll get started. So y equals x plus 4, y equals x squared minus 2x. Now, when we're trying to find these areas, I typically set up the area between the two curves, or ask you to find the area between those two curves by looking at the area of one rectangle first. So let's figure out the area of that one rectangle. And I know in this case, it feels like we're slowing down just to take and find the area of this one rectangle, but this little slice here, which I'm going to give a thickness of dx, that little slice is going to become more important as we work with things in section 6.2 and 6.3. So, okay, let's find the area of one rectangle. That's going to be top minus bottom times the thickness, which is your dx. That's how wide that little slice is. Now, I like that we put this notation here, dx, because that reminds you that this function here, or this difference, better be in terms of the variable x, because that's what we want to integrate with respect to. So our top function is x plus 4. Our bottom function is x squared minus 2x. And here's an easy place where people make a mistake. Can you see my mistake here? What's my mistake?
You need a bracket.
Yeah, I need parentheses around this. Okay, because that negative has to distribute itself to both terms. So this is something that happened to me last semester all the time. It drove me nuts. People had the wrong expressions, but miraculously they came up with the right answer. And that kind of made me a little bit nervous. But that's not going to happen this semester, because I know you guys are going to rock on this. If you distribute that negative and then collect like terms, that becomes negative x squared. And then we've got like terms here and here. So let's combine the like terms. Plus 3x plus 4 times dx. Okay, that's fine. Now, we need to know where to integrate it. I suppose if I click on my picture, I can figure it out pretty easily. But let me also advise you that sometimes you may not be given this information. You need to figure it out yourself. And so what you're going to have to do is you're going to have to set these two equations equal to each other and solve. So let's solve x plus 4 equals x squared minus 2x. This is a quadratic equation. I hope that you're comfortable solving quadratic equations. So if I factor this, it's going to factor as x minus 4 times x plus 1. So cool. So it's telling me that these two curves intersect at x equal 4 and x equal negative 1. So let's draw that here, negative 1 and 4. And those are important because they tell us the limits of our integration. If we're going to add up all these imaginary rectangles from the lowest to the highest, we need to know where those go. And in the x direction, that's between negative 1 and 4. So negative 1 to 4 of negative x squared plus 3x plus 4 dx. How's that looking so far? I mean, if you get here, you're pretty much golden. I'm hoping that the rest is not too bad. Okay. Couple things. Now, I'm sure we'll do one where it's not a nice, easy polynomial, but you know what? A lot of times I'm going to ask you finish these problems with fn int as a numerical function on your calculator that'll evaluate things like this. Let's see what it gives us. So, you know what? Let me do it this way so you can maybe see better. Can everyone see my graphing calculator here? Can someone see my calculator?
Yes.
All right. Thank you, John, Carl. So to help you out, hit the math key. Math 9. Oh, isn't that special? We want to integrate from negative 1 up arrow to 4, right arrow to the argument. So that would be negative x squared plus 3x plus 4. Then, of course, you got to tell it dx. Now, I guess what I like about using this TI graphing calculator emulator is that it shows you all the keystrokes that I've used. That way, if you want to go back and try and do this for yourself, you can. So 20.8333, that sounds like 5/6 there. So if you hit the math key and press enter twice, it'll turn that into a fraction. Generally speaking, I want fractions when you're all done. So let's just write 125/6. I don't want decimal values. And by the way, sometimes when you do this, you don't get an exact decimal value just because your graphing calculator can't do things like we do. So, okay, good deal. How's that one looking? All right. Let's try one or two more. Unless there's something on this one that I can, help out with the confusion.
Oh, I wasn't sure if you had this on the syllabus, but what's your calculator policy? Like, does it have to be a TI?
No, it does not. It does not.
Okay.
The unfortunate thing is that, while there's a lot of the great calculators, Casios, Hewlett-Packard, Sharp, or a TI Inspire, I don't know most of those very well. So as far as some of the commands, you're going to be kind of on your own. So,
okay.
But if you're comfortable with that, that's great. If you remind me with an email, I think there's a place to get this little graphing calculator emulator. I think Texas Instruments made it available on kind of like a 6-month courtesy basis just because of this COVID stuff. So it's very nice of them to do that. I'm sure it's costing them some money, but it also feels like the right thing to do. So good on them.
Okay, thank you.
You're welcome. Do most of you have a TI? Some of you got some other stuff going? Okay. Let's try problem number 4. Problem number 4 is going to be a little bit interesting. It's graphed for us in the book. And what's a little bit interesting about it is the fact that these curves aren't curves of y defined in terms of x, but it's x defined in terms of y. So a little bit more different than what we usually get. Now, if you're thinking, oh, well, I'll do things in this direction, that works to an extent. But the problem with taking a dx slice here is that, your top and bottom function are consistent for part of this region. But when I get over here to the x-axis or the y-axis, my top and bottom function are the same. How do you subtract top minus bottom when it's the same function? Same thing over here. So it makes taking a dx slice really difficult. So what else could we do other than take a dx slice? How about if we took a dy slice? How about if we slice things horizontally? And the nice thing is that our rectangles then are always going to be the same form. Right minus left is going to be the width of your rectangle. And your expression for right minus left is going to be consistent from top to bottom in this function. So let me draw this as best I can. And we'll figure out the area between those two curves. So let's see. There's that one. And something like that. So, okay. And we'll draw our little y-axis here. This is x equals 2y minus y squared. And this one up here is x equals y squared minus 4y. Oops, x equals y squared minus 4y. All right. So we want to find the area between these two curves here. Can you see the disadvantage of trying to do this with a dx slice? You'd have to really do it in 3 regions, and even then, it'd be difficult, really difficult to try and characterize, well, what's the height of this? Top minus bottom, well, you have a function to itself. It'd be a real pain. Maybe you could do it. I don't know. Not sure I'd want to try and do it. But if we take a horizontal slice, then things are a little bit more friendly. So let's take a slice like that. So here we go. There's our slice. And because it's horizontal, we'll call that dy. Let's find the area of one slice. Well, that's going to be the width area. It's going to be the width times the height. The width is going to be the rightmost portion of your function minus the left. Right minus left. And the height, this height is just going to be your dy. But that dy is telling you that this stuff here better be functions of that same variable. Better depend on y. So the rightmost function, that's this one, 2y minus y squared, minus the leftmost function, that's this one, y squared minus 4y. If you notice, I was careful to put parentheses around both of those. Let's distribute 2y minus y squared plus 4y. And we'll clean it up. Minus 2y squared plus 6y. Nice. So that's the expression that we're going to integrate. Negative 2y squared plus 6y dy. But the question becomes, well, okay, where do we integrate from and to? And the book provides partial answer here because they give you the coordinates of this point of intersection. Now, that's something I expect you to be able to find. What you would do is you would set this expression equal to that expression and solve. And you'll get two answers. One of them will be 0 and the other one will be 3. When you put in y equals 3 here, you'll get x equals negative 3 because you'll end up with 9 minus 12. So it'll be negative 3. So negative 3 and 3. That's that point. And of course, down here, that's the origin, 0, 0. So one of the little things I do for partial credit is I see, do you have the proper limits of integration? What are they here? What should I integrate to and from?
3 and 0.
Good, good. So 0 here and 3 here from bottom to top. Thanks, Kamaya. So 0 to 3. And let's actually do this one out. So that's going to be negative 2/3 y cubed plus 3y squared between 0 and 3. So negative 2/3 times 3 cubed plus 3 times 3 squared. That's our upper limit. At the lower limit, this function is 0. So let's see, that's going to be negative 6 plus 27. I'm getting 21. All right. Not bad. Not bad. How are we looking on that one? Good. All right. Let's do one more. Are you guys seeing the difference why we took a dy slice here as opposed to a dx slice? Because when you're trying to take your slice, if you end up with top and bottom functions are the same function, that's going to be a problem. You need those to be different. Like here, top and bottom are different here. They're different functions, but not in this little part and not in this little part. So that's why we had to change things up. Let's do one more and then we'll take a break. Typically speaking, I want to take 3 breaks, 3 kind of quick breaks, because I know this is a long class and you know, you need to recharge. I get it. So, let's take a look at problem number 24. That's 24 if you actually had a physical copy of the book. So it's going to be y equals cosine of x and y equals 1 minus cosine of x. So I think that's going to look like a big pair of lips in kind of a profile way. But let me just double check that with the graph. So if you haven't figured it out yet, you will soon. I really like Desmos. It's a cool program. So let's take a look at both of these graphs. Y equals cosine of x and y equals 1 minus cosine of x. There we go. And so what we want to try and find is the area between these 2 curves. So let's see, did they give us any more of a clue here? Oh, they want it between 0 and pi. Okay. That's fine. That's a little strange. Okay, we're going to have to think about that a little bit. So let me put on a couple restrictions here. If you use that curly brace, 0 less than or equal to x less than or equal to pi, that gives us a restriction there. And then here. So I want to find the area between these 2 curves. Now, one thing that I want to emphasize for you is that the area between 2 curves is going to be positive. And so we're going to have to be a little bit careful in this one as to how we do it. So let me try and copy this graph to my sheet. You might want to do the same. Oh, so let's just do one thing here. There's one thing that I think I want to know, and that's that point of intersection. Anyone want to guess what that point of intersection would be before I click on it and do the big reveal? Too late. Pi over 3. So there we go. Pi over 3 is that magical point. And of course, we're going to extend our graph out to pi. Okay. So this first function here, this top one here is y equals cosine of x. And then the other function here is y equals 1 minus cosine of x. I wish I would have drawn that someplace else. It's okay. So kind of like our previous problems, we need to find the area of one slice here, like that. What's the thickness of my slice? Is that a dx slice or dy? Thank you, Michael, dx. All right, so area of one slice. Okay, so it's going to be top minus bottom times the thickness, top minus bottom times, let's just put it in right away, dx. Top function is cosine of x minus the bottom function, and you got to put that in parentheses. And when you simplify it, we end up with 2 cosine of x minus 1 times dx. Okay, that's what we want to put in our integram. 2 cosine of x minus 1 dx. But if you put limits of 0 to pi, you'll get it wrong. Why is that?
They cross each other?
Yeah, they cross each other. So your top and bottom functions flip after this point. In fact, here's a little experiment. This is something I saw a lot last semester. People would do some problems like this and get a negative answer. When you're trying to find an area between two graphs, let me tell you in no uncertain terms, it should be positive. If you get a negative, there's something wrong. If you can't find it, at least write a note to you saying, all right, I know I'm getting a negative answer, but it should be positive. I can't find my mistake. I'll give you more sympathy and partial credit than I would if you just give me a negative answer. You shouldn't get a negative answer for something like this. So good job, Amar. We're going to integrate between 0 and pi over 3. That's going to give me this area. Call it A1 if you want. But we also have to add in another integral. What's that other integral going to look like? Well, let's figure it out. Area of 1 slice.
Minus 2 cosine x.
Exactly. It's just going to be the opposite of that. You're going to end up with 1 minus cosine of x minus cosine of x dx, and that's going to simplify to 1 minus 2 cosine of x. Between pi over 3 and pi. Yay. Okay. This setup here is what's most important. Are you comfortable with the setup here and why we needed to switch things up? So a decent graph is a valuable asset, because without that graph, we wouldn't realize we need to flip things up. But if you just integrate this from 0 to pi, my guess is you get a negative answer. Let's just check it out. Now, one thing's wrong with my calculator at the moment. It's in degree mode. What's calculus done in? Radians. So make sure your calculator is in radian mode. Leave it there for the rest of your life. All right, kind of kidding on that a little bit. But my guess is if I just type in 2 cosine of x minus 1 dx, I'd be surprised if we didn't get a negative number. Yeah, we do. We get negative pi. Whoops. Shouldn't get that. All right. So really, we should only run that first integral between 0 and pi over 3. I'm kind of curious what that would be. Let me see if I can figure it out. Man. Nope, can't figure that one out. All right. I'm just going to worry about the setup for this one. Are we okay with the setup? I want to get you a quick break here. All right, when we come back for break, I'll try and have the answer to that calculated. So, okay, give yourselves a good 6 minutes to relax. We'll see you in a few.